Today we're going to cover the first part of Chapter 5 and talk about stereoisomers. Now we've already spent some time looking at isomers. Isomers in general, the general equation for isomers are different compounds that have the same formula, and we're going to break them up into two categories today. Constitutional isomers, these are molecules that have the same formula but different constitution or order of connectivity of atoms. And we're going to talk about stereoisomers, the same molecular formula but different spatial arrangement of atoms. So constitutional isomers are going to have a different sigma bonding framework, whereas stereoisomers have the same sigma bonding framework, the same skeleton, it's just they have a different orientation in space. So the first example that I want to share with an example of stereoisomers is the connectivity around a ring. So we have two versions of cyclohexane here, both with two methyls on them. On the cis version of the cyclohexane, the 1,2-dimethyl cyclohexane, we have both methyl groups on the same side of the molecule. And you can see we have our projection here with the wedge for both methyls, indicating that those methyls are coming towards us. They're coming out of the computer screen towards us, compared to the trans, where we have one methyl group that's coming towards us and one methyl group designated by a wedge that's going into the plane of the screen. So we can look at them from this angle, and from this angle we see both methyl groups on the top side of the ring, the top face of the ring, both hydrogens on the bottom face of the ring. And for the trans stereoisomer, we have one methyl group on the top side of the ring and one methyl group on the bottom side of the ring. So while these two molecules have the same atom-to-atom connectivity, the same sigma bonding framework, their orientation in space is different. Another example where we have stereoisomers are going to be our alkenes. In an alkene, we have a pi bond. And this pi bond is built by overlapping p orbitals. Now, because of this pi bond, the sigma bond does not have free rotation. So whatever conformation the molecule is in around this double bond, we can't rotate. So therefore, we could have, if we have butane here, cis-2-butene, right? We have 4 carbons, and we have a methyl group on either side of the double bond. And there's two stereoisomers. The cis-butene has both methyl groups on the same side of the double bond, and the trans-butene has the methyl groups on the opposite sides of the double bond. So this methyl group is on the same side of the hydrogen, and this methyl group is on the same side of this hydrogen. So again we have the same connectivity, right? This carbon is connected to this carbon all the way through, but in space we have different arrangements. So stereoisomers are going to lead to a new concept that we're going to learn about, which is called chirality. So we can identify a molecule as chiral, and if a molecule is chiral, that means that it is asymmetric. The easiest way to describe chirality is to look at your hands. So if you hold your hands in front of you, your left hand and your right hand are mirror images of each other. But if you try to place them inside of each other so that there's 100% overlap, it doesn't work. They're non-superimposable. If you turn your right hand over, place it on your left hand, they're not going to fully encompass each other. It can never happen. So this type of test, this handedness test, is what we can use for a molecule to determine if it's chiral. So if you take a molecule, we have this molecule on the left hand here, and you draw the mirror image of the molecule, then no matter what angle you turn those molecules around to, you should never be able to superimpose. And this is easier to view with a model kit, because you can build a molecule and you can build the mirror image of the molecule and you can try to superimpose them. But if you try to superimpose them, you'll never get 100% overlap. And if that's the case, then you have an asymmetric molecule that is considered chiral. we can look at this molecule here. This atom has 4 different things attached to it, and that's going to be a key to assessing whether a molecule is chiral or not. We need to have a carbon with 4 different substituents attached to it for it to be chiral, for it to be a chiral center. So this molecule here, very small and simple. We can take the mirror image of it, and we notice that this carbon has 4 different things attached to it. But we can take the mirror image of it here, and if we were to turn this molecule, the methyl group would be where the ethyl is, and the ethyl would be where the methyl is. But these are different molecules that have a different orientation in space. So the relationship between 2 molecules of this nature is called, they are a pair of enantiomers. So enantiomers are 2 molecules that are mirror images but not superimposable, therefore not identical. And for a molecule to have an enantiomer, it must be a chiral compound. So we can take a look at this molecule on the left here. Right? This is a chiral compound. We can just draw the mirror image of it, and it's an enantiomer. Now, let's take a look at this stereocenter here. We have a carbon. Attached to it is a chlorine. This carbon's making 3 bonds shown, so we can assume that there's a hydrogen attached. That's going to be a dashed hydrogen going towards the back. And there's a methyl group and an ethyl group. So this carbon has 4 different substituents attached, and the mirror image of it will be its enantiomer. Now, we drew the mirror image of it this way, but we can also draw it this way. Here, instead of having the stereocenter indicated with a wedge, it's indicated with a dash. And if we were to take this molecule and flip it around, it would match the molecule on the previous slide. So using the wedge dash notation makes it much easier to indicate a change in the stereocenter. So for example, with this molecule here, we're able to indicate that there's a different stereocenter because the methyl group is wedged on the left molecule and dashed on the right molecule. The first tool that we're going to need to learn for dealing with enantiomers is the changes to our naming scheme to account for this. And so we kind of looked at this with the game that I showed in class, but enantiomers are going to be completely different compounds, so we're going to have different names for them. And so we're going to either have the R configuration at the chiral center or the S configuration at the chiral center. And a pair of enantiomers will consist of a molecule that has an R stereocenter and one that has an S stereocenter. So to begin with, for the naming, we're going to use the atomic number to prioritize the 4 groups attached to the chiral center. So for example here, chlorine has the highest atomic number. That'll be a 1. Hydrogen is always the place I like to start because it's always going to be the lowest atomic number. We'll designate that as a 4. So hydrogen will always be 4. If there's 2 hydrogens, then it's not chiral because we don't have 4 different substituents attached. Oxygen is the next highest atomic number, and then followed by carbon. So once we've prioritized every single one of the substituents, we're going to orient the molecule or rotate it, turn it, so that the 4, whatever the 4 is going to be a wedge. We want the 4 to be facing away from us. And then we can count the priorities, 1, 2, 3, to determine the order that they're in. So here, 1, and then to the left is a 2, and then here's a 3. So this would be, if we envision this as a circle, it would be counterclockwise. So counterclockwise is always S, clockwise is always R. The way I remember this is that clockwise, or R, would be to the right. R to the right. So in this specific molecule, we have a 1, a 2, and a 3 with the 4 in the back. We'll be going to the left, or counterclockwise. and so therefore it will have the S conformation. So sometimes we might have the same atom attached in two different positions. Let's take a look at this molecule. We can easily identify the 4 as being the hydrogen. Remember, the hydrogen is almost always going to be the 4 if there's a hydrogen attached. And we can identify the 1 as the oxygen because it has the highest atomic number. But we go to each side here, and we have a CH2. Now you might say, hey, we have the same group attached. This can't be chiral, but that's not true. We have to keep moving further away. So this carbon has 2 hydrogens attached. This carbon has 2 hydrogens attached. These two are tied. So if we step out one further carbon, this carbon has 2 carbons attached and a hydrogen, whereas this carbon has 1 carbon attached and 2 hydrogens. So this is the tiebreaker. On one we have a carbon relative to a hydrogen on the other, so the left side here will take the highest priority. We have to compare the atomic weights of the atoms bonded to as we move further out to make the tiebreaker. And we can go through each layer as needed. So in the first layer, we designate a hydrogen at 4 as the lowest priority, oxygen at 1 as the highest priority. Then we go to the second layer, and we see they're both carbon, so we're going to have a tie. So then we have to decide what is attached to each of those carbons. On the right side here, we have 3 carbons attached, and on the left side we have oxygen and 2 hydrogens. Because we have an oxygen attached and it's the highest atomic number, that's going to be our tiebreaker. And the left side here will have the highest priority. If we run into an example where we have a double bond, so for example this molecule, the double bond counts as having 2 bonds to that atom. So this carbon would be, the way we would count this carbon is bonded to 2 oxygens and a hydrogen. Sometimes it's actually easier, instead of flipping the molecule around and putting the 4 in the back, to just analyze the conformation with the 4 in the front. So that way you don't have to move the molecule around. And you can do that, but you just have to keep in mind that you're approaching it that way. So if we switch the molecule so that the 4 goes into the back, right, we would have an S conformation here. 1, 2, 3, it's counterclockwise. If we took the same molecule and we had the 4 coming towards us, it would be the R conformation. But we can put the 4 coming towards us and then just use the opposite of the orientation in order to designate R versus S. And if you switch 2 groups, like if we were to switch the 1 and the 4, for example, here, it goes from S to R. But we can use this trick of switching the 2 groups to help us determine if it's S versus R. Now, if we switch 2 groups twice, it returns to the original conformation, but it allows us to put the 4 priority group in the back. And so you can do that as well. There's a few different tricks that you can use. There's different ways to approach it. The best way is to find the approach that works well for you, and then use the same approach over and over again, and stay consistent. Personally, I like to use the approach where we put the 4 in the back and then determine the rotation of the 3 in the front. So to summarize the rules, the first step is to identify the 4 atoms attached directly to the chiral center and then prioritize each of those atoms based on the atomic number. If we have 2 atoms with the same atomic number, then we stepwise move further and further away. We're going to rotate the molecule so that the 4th priority is on the dashed line so that it's going away from us. And then we determine if the 1, 2, 3 sequence rotates clockwise or counterclockwise to designate R versus S. And so once we've done this, we can name the molecules. So this molecule is 2-butanol. And if we use the system, we would designate this stereocenter as R. So then our naming convention would be R2-butanol. Similarly, it's enantiomer. We'll have the inverse stereocenter, so it would be S2-butanol. There are some cases where we will have multiple stereocenters, and so this 3-methyl-2-pentanol here is going to have 2 different stereocenters attached to it, and so we would find the stereochemistry of each stereocenter. So the first stereocenter will be R, and then the second stereocenter would be S, and so it would be 2R, 3S, 3-methyl-2-pentanol. So you can try this problem for practice. Identify all the chiral centers in the molecule. Remember, they're going to be centers that have 4 different substituents attached. A methylene will never be a chiral center. A methyl will never be a chiral center. But when you get to a point like this, we have visibly 3 different things attached here, right? 3 and 5 are different. This is a propyl group. 5 is going to lead to all this other part of the molecule. And we can assume there's a hydrogen attached. So this would be a stereocenter at position 4. Methylenes, CH2s, never stereocenters here. We hit a carbon that has 4 carbons attached, and all 4 of the carbons attached are different from each other. They each have different things attached to them. 8, we have an NH2 attached, a carbon and a carbon. These 2 carbons are different from each other, and there's an implied hydrogen attached. So this would also be a chiral center.